Okay, this is a scenario that's going to help us understand when we get to use central limit theorem and the shapes of the distribution, etc. So the distribution of household incomes in the United States is skewed to the right. It's highly skewed to the right because of the upper incomes. The population average is 71,500 and the standard deviation of the population is 26,000. So we basically say that we have a mean of the population of 71,500 and a standard deviation for the population of 26,200. A sample of 100 is taken. So I've taken a large sample. My sample size is greater than 30. What is the shape of the distribution of these sample values along with the mean and standard deviation of the distribution of the sample values? Now we got to be careful. They said the distribution of the sample values. They did not say the distribution of the sample means. That's the difference. They said sample values as opposed to sample means. So consequently, they're talking about what is the shape of the underlying distribution. Well, the underlying distribution is skewed to the right because we already stated that earlier, with a mean of 71,500 and a standard deviation of 26,200. Had they talked about the distribution of the sample means, we could have used central limit theorem because the sample size is greater than 30. But in this case, the distribution of the sample values always follows the distribution of the population. This is always true for sample values. So the individual values or the individual scores will always follow the underlying distribution, and the underlying distribution is skewed. Distribution of sample means becomes normal if, or approximates the normal, if n is 30 or larger. The next one, a sample of 25 is taken. So now we're not large enough. In this case, n is less than 30. So it's not big enough. What is the shape of the distribution of the sample means along with the mean and standard deviation of the sample means? Well, it is skewed right, but it's getting closer to the normal, but it's still not normal. All right, it's still not normal. It's less skewed to the right. And if you just wrote not normal, that would be fine. And it's not appropriate to use the distribution of the sample means because the underlying population is not normal. All right, if the underlying population was normal, we could say, hey, it's normal. And the sample, but in this case, it's not normal, and our sample size is less than 30. We cannot use central limit theorem. However, mean still hasn't changed, 71,500, and our standard deviation is changing. It's 26,200 divided by n, because remember, distribution of the x bars is always follows this. It's just we don't get to use the normal values if our sample size isn't large enough or the underlying population is not normal. Okay, so now we take a sample of 110. Well, this is clearly large enough. What is the shape of the distribution of the sample means? All right, so here we're looking at sample means versus up here we were looking at sample values. Because we're looking at the sample means, we now can use central limit theorem. So the shape is approximately normal, and really I should have used the word approximately, so please make sure that you do. The distribution of sample means is approximately normal because n is greater than 30. So our mean is 71,500 and our standard deviation is 26,200 divided by the square root of 10. Once again, x bar, standard deviation of x bar is the standard deviation of the population divided by the square root of n. A sample of 50 is taken. What is the distribution of the x bars? Well, they're asked, when I say x bars, they're saying the sample means along with the mean and standard deviation. Well, this is greater than 30. So, and by the way, it can be greater than or equal to 30. Because it's greater than 30, it's normal by central limit theorem, even though the underlying distribution is skewed. It's nice, the mean is always the mean. We don't have to worry about that. And we have 26,200 divided by the square root of 50. And there we go. So what is the probability that a household is randomly selected from the population and earns more than 95,000? Well, keyword A, this is a singular value. Well, this is skewed data, so I can't use the central limit theorem because I only have a sample of size 1. So the distribution of the population is skewed, and I cannot use the distribution of means because my sample size is 1, which is less than 30. Now, if they said, hey, what is the likelihood that 30 households had an average greater than 95,000? I could, but I would need be talking about the averages or the means, and I would need to have a larger sample size. Then it says, what percent of households earn between 55,000 and 85? Once again, our distribution is skewed, and I do not have enough information to determine the probabilities. Now, if it had, so I cannot use the distribution of means because it's asking about the distribution of actual values. If it says, what's the probability that in a group of 100 households, the average is between 55,000 and 85,000, then I could, but I can't do it for an individual values. And it says what percent, how many houses is basically it asking. So how many single households earn between 55 and 85,000? So I can't do it. Okay, so central limit theorem. Sample size must be 30 or larger, or the underlying population must be known. The mean is always the mean, and the standard deviation is the standard deviation divided by the square root of n. And that's even really true for a sample size of 1, because really 26,200 divided by the square root of 1. So basically, all of them are really divided by the sample size. But it only becomes impactful when it's not 1. And we must have, to use central limit theorem, we have to have a sample size of 30 or larger, and or we have to have an underlying distribution that is normal. Okay, with underlying distribution of normal, we don't care what the sample size is. We can use the normal percentages. Thank you.